Good day and welcome to yet another of our presentation in inorganic chemistry. Today we want to take a look at the valence bond theory. Before we start, I would wish to direct you once again to look at our earlier post on Introduction to Coordination Chemistry on our YouTube channel, QuantSpec, where we discussed exhaustively the basic types of chemical bonding. Valence bond theory discusses covalent bonding. Remember, we had said you have ionic and covalent, and within covalent, you have true covalent and dative covalent. So, for this reason, when we say valence bond theory and we mention covalent, you should have in mind that we are also talking about dative covalent as discussed by valence bond theory. The basic principle of valence bond theory is that covalent bond is formed by the overlapping of two or more orbitals of atoms bearing at least one electron. One electron must be carried by an orbital that is ready to bond. And as the orbitals approach each other, they overlap such that a molecular orbital is formed, and the single electron that the orbital contains shall now constitute a molecular orbital. It was before now atomic orbital electron. Upon the formation of a molecule, as you have oxygen molecule, hydrogen molecule, water molecule, there shall be a formation of a molecular orbital to convey the electrons that were contained in the atomic orbitals. As you can see, as you can see in this schematic, we show you that there are two atoms here, atom A and atom B. Atom A and B shows valence orbital or valence shell on the outer layer, which is marked red, and they contain paired electrons, except the red electrons that are single electrons. And as you know, electron must come in up and down spin. And because the electrons are single, they need to pair up so as to be able to form a bond. And if you watch carefully, you also see that the paired electrons are 6 plus 1, 7, meaning that the atoms have not completed octet. And for the atom to complete octet and assume the electronic configuration of a noble gas, the two red electrons must pair up, as you can see down there. And because these atoms contain more than four electrons in the valence orbital, they are electronegative, and they will pair up to form a covalent bond. They will pair up to form a covalent bond. As you can see, when they form the covalent bond, a molecular orbital, as you can see in the green orbital in the outer layer, there is a green orbital encompassing the two atoms, carrying the two red electrons. These two red electrons are shared by the two atoms. And at that, we now say that a molecular orbital has been formed and the atoms have bonded. The same applies in the formation of a coordinate bond. But the difference between the true covalent and the coordinate bond is that one of the atoms would have a vacant position where the other atom will share its two lone pair. As you can see, there are two red electrons to the right, two red electrons on atom B, while there's a vacancy on atom A. The position of this vacancy allows for the bonding. The two red electrons here, one shall be sent into this vacant orbital and there shall be a bond. As you can see, a dative covalent bond is formed here. A dative covalent bond is formed as it joins the two electrons together. So that is the situation where we talk about true covalent and dative covalent bond. Further on, we can explain this by bonding two atoms of hydrogen, two atoms of hydrogen. You can see the black hydrogen and the red hydrogen. The colors are only used to differentiate the two bonding hydrogen. The black hydrogen has a black 1s electron in the s orbital, and the red hydrogen has a red 1s electron, and they need to pair up as we had said already. So at this point, you realize that the two s orbitals, the two 1s orbitals will blend to form a molecular orbital bearing these two electrons, the black electron and the red electron revolving around the molecular orbital. That is the point that these two, the black and the red hydrogen shall bond to form hydrogen molecule. The same applies in the formation of water. For you to form water, hydrogen will bring its one electron and it will overlap with the one electron, the orbital will overlap with the one electron orbital of oxygen, as you can see in the structure, H2O, H2O. 2H will bond to one oxygen to form a water molecule. Go ahead. What are the assumptions of the valence bond theory in coordination compound? In covalent compounds, where we talk about true covalent, and in true covalent, as you have explained already, we are talking about a situation where every of the participating atom must contribute at least one electron. Each combining atom contributes orbital bearing at least one electron to overlap with the other, and the overlap will yield a molecular orbital, which will now allow the said contributory electron to revolve around it. There is a slight difference when we talk about dative covalent bond or coordinate or complex bonding. This principle varies in that the one of the atoms, which is usually the metal center, which assumes a positive position, will yield or provide either an S, a P, or a D hybridized degenerate orbital. Hybridized, a mix. By hybridization, we mean a mix. The orbitals must mix so that they assume a common energy level. They assume a common energy level to allow for bonding. So when hybridization goes on or it takes place, there shall be a degenerate. Degenerate meaning at the same level. Assume they must not be 6 for 6. It can be 6.4 and 7 or 8 and 9 as the case may be. This sums up the hybridized orbital will sum up to give you the total number of coordination that the metal center can take, which we call the coordination number. Every atom has a definite number of ligand or anion that it can accept at a particular geometry. And a ligand too must possess a lone pair electron that it is willing to contribute. If it just possesses lone pair electron and is not willing to contribute for the bonding, then there shall be no bonding. So the metal must have empty orbital, the ligand must have lone pair electron. The vacant hybridized degenerate orbital of the metal center shall overlap with the orbital of the ligand to form a dative covalent bond or coordinate bond equal to the number of the metal center coordination number to depict a regular geometry. We're going to take time on this slide to show what we mean. If we consider cobalt 27, You will recall that cobalt, in our introductory slide, we told you that cobalt will show 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7 configuration. But for the purposes of this lecture, we have brought down 3d7 to be at par with its three quantum state counterparts. For cobalt to form a plus 3 state, cobalt must lose three electrons, two electrons from the 4s and one electron from the d7. So you can see that the orbital to lose the electrons have been marked with a red star. The red star shows you that that orbital will give out its two electron and its one electron. At that point, you are able to generate cobalt 3 plus. And in our discussion, we have shown that when 4s2 loses its two electron, it shall assume the green status. The green status means that it is blank, it no more contains electrons. And we had already told you earlier that the metal must contain vacant orbital. So the vacant orbital here is as a result for the S2, for S2, is as a result of the loss of the two electrons there. That's why we put the red star and the red star. The two electrons here and the one electron here will be lost. And when it is lost, it shall generate one S in the 4 and 2D. 2D, the second D is generated when the single electron here is caused to pair up with the single electron to the left. So you now have one S and two Ds, but cobalt needs 6. So you will now see that in so long as there was a 4 quantum state, there must be a 4p and a 4d. So at this instant, we're going to have ammonia bonding to cobalt 3 plus through the 4s empty and the 3d empty, 2 of the 3d empty and 3 of the originally not occupied. The three blue orbitals here, the three blue orbitals shown up here were not occupied at all. All the electrons ended up in the 3d7. So we're going to have 4s, 3p, and 2d, 4s, 3d, and 2d, and 3p. And these are where you have the six ammonia, the 6 ammonia molecules bonding to form hexaamine cobalt 3 and in an octahedral. If you add S1, P3, 4, D2, 6, and you can see ammonia 1, ammonia 2, ammonia 3, ammonia 4, ammonia 5, and ammonia 6 as shown by the blue S orbital overlapping with cobalt. So at this point, they form a regular geometry, regular octahedral geometry, which is equivalent to the sp3d2 hybridized configuration. Further on, we want to look at different hybridizations and their resultant bonding geometry. If an atom has an sp, S and P only used in bonding, as you can see in the first structure up there, the blue and the two white are linked up by two bonds, and you can clearly see that it is linear in nature. But if it is sp2, you realize that there are three whites linked to three ligands linked to the blue metal center, and you call that trigonal planar. It is in a planar form. You see, when you are discussing geometry, you must be able to conceptualize the three-dimensional view, the 3D view. You must be able to conceptualize it. And we move further to the DSP2 or SPD2. DsP2 mean that D is coming from a lower quantum state, say the 3D, 4s and 4p. Or you also have the SPD2. SPD2 mean they are on the same level. So this one is an inner sphere, while this one is an outer sphere. You have the outer sphere because they are on the same quantum state, or the inner sphere because one of the bonding orbital is on the lower quantum state. And at that point, there are four: D1, S1, P2, meaning 1 plus 1 plus 2 equals 4. And because it has this disparity, the D2, the DsP2 or SPD2 will yield a square planar pointing to the apices of a regular square or rhombus, as you will call it. It points to a regular square, as you can see by the structure. There is also the sp3. The three p here are of the same energy level. So sp3 shall yield a tetrahedral. sp3d shall yield a pyramidal, while sp3d2 shall yield an octahedral, as we have already seen. We wish to show this by electronic interaction. Now, if we look at silver, silver has a 4d and empty 5s and 5p orbital. As you can see, silver plus 1 has 4d field and empty 5s, empty 5p. So this empty 5s, only one s and one p is used, and you call it an sp hybridized bonding orbital, and it is the hybridization is taken over by two ammonia molecules. Having been taken over by two ammonia molecules, it results to an sp geometry that is linear in nature. The same applies here. Zinc takes over four ammonia molecules, and the four ammonia molecules is taken by the 4s and the 3p's. So it becomes sp3. sp using one 4s and three 4p's. The three are on the same quantum state. We had said this earlier. So because it's sp3, a uniform s and a uniform p at the same 4 level, it becomes a tetrahedron. As we had discussed earlier, the DSP2, here you have, it is using it is using 4. DSP2, it is using 4 to bond, and you have it as tetracyanonickelate 2. Tetracyano nickel, you had lost 2 electrons and became nickel 2 plus. The same applies when you're talking of trigonal. So the electronic display here tells you the square planar, trigonal, and two octahedral here indicated. What are the merits of valence bond theory? Valence bond theory has satisfactorily explained the formation of covalent bond and been able to convince of us of the geometry of most of the molecules so studied. It has also accounted for the variation in bond length. The greater the overlap, the shorter the bond, and the stronger, therefore, it can determine the energy of the bond. The closer it is drawn, remember, the shorter the bond, the stronger the bond, and the higher the energy. And it can also account for the magnetic properties of the compound. Anyhow, as it is always the case, the assumption of electrons in a fixed position is misleading because electrons are never fixed. Electrons are perpetually in a state of motion. But this theory assumes that an s electron remains in s orbital, a p electron remains in p orbital. No, it is misleading. It has not been able to quantify the stability. In spite of the fact that it is able to account for bond length and bond energy, it has not been able to tell us how stable a certain coordination compound is. And it has not been able to account for the color, the spectral property of coordination compound has not been accounted for by valence bond theory.